Welcome back to the Deep Dive. Our mission today is a full immersion into the cosmos, but we're hitting two very different depths of knowledge.
That's right.
We are going to start by tackling the astronomical myths and misconceptions, the things we think we know, but often, profoundly misunderstand. And we're using hard scientific evidence to set the record straight.
And once we've anchored ourselves in that established certainty, we're pivoting to the genuine frontiers of the unknown. We're moving straight into the most intriguing open questions in astrophysics.
And that's where things get really interesting.
Exactly. We'll be looking at everything from these hourly repeating signals detected near the center of the Milky Way to potential clues for dark matter, all the way to, the most baffling near-perfect alien signal ever received.
We've gathered material that challenges common assumptions, but that also takes us right to the cutting edge of current research. So think of this as a shortcut to being well-informed on both the fundamentals and the latest anomalies.
It's so vital to do that groundwork first. I mean, so much of astronomy feels counterintuitive to our day-to-day experience here on Earth.
Totally.
We have to debunk the myths first so we know where the science truly ends and where the mystery begins.
Okay, let's jump in.
Let's do it.
So we're starting with the object that everyone observes, and yet nearly everyone misunderstands, the moon. It seems so familiar, but the simple concept of lunar rotation is a stumbling block for so many people.
It's the perfect example of how an accurate observation can lead to a completely incorrect conclusion.
Okay, what's the observation?
The observation is simple. We, here on Earth, always see the exact same face of the moon. Always. I mean, from a purely visual standpoint, the features, the craters, the dark seas, they never change their position.
Right. The man in the moon is always looking at us.
Always. So the logical but flawed conclusion is, if we only ever see one side, the moon must not be rotating relative to us.
But the truth is, it is rotating.
Okay.
It's just, you have to shift your frame of reference. The analogy I love here is the waltz.
That's the best way to visualize it. This idea of a synchronous orbit. Imagine you are the moon and your partner is the Earth.
Okay.
As you complete one full circle, one full orbit around your partner, if you want to make sure your partner never sees the back of your head,
You want to always be facing them.
you have to complete exactly one turn around your own central axis during that orbit. If you didn't turn at all,
They'd see your back after half the dance.
exactly, to maintain that lock, you have to rotate precisely in time with your orbit.
And there's a physical reason for this. It's not a coincidence.
Oh, not at all. It's called tidal lock, or gravitational capture. Early in its history, the moon's rotation was likely much faster, but the Earth, being so much more massive, exerted these immense tidal forces on it.
Like a giant break.
A colossal break. It just stripped the rotational energy from the moon over millions of years until its rotation period perfectly matched its orbital period, about 27.3 days.
And once you get your head around that, the next big confusion, the lunar phases, becomes much easier to understand.
It does, but they are often confused. The phases are, I think, the most widely taught yet still misunderstood astronomical concept. The common misconception, which you still see in textbooks,
Oh, I remember this.
is that the phases crescent half gibbous are caused by the Earth's shadow.
Right, like a crescent moon is just the Earth partially blocking the sunlight.
If that were true, we would be having a lunar eclipse every single month.
And we don't. Eclipses are rare.
Exactly. A lunar eclipse is a special alignment, happening maybe once or twice a year when the sun, Earth, and moon line up perfectly. A phase is just an everyday event.
So what's the scientific reality?
Simple geometry. The moon is a sphere. The sun always lights up one full half of that sphere. That's the moon's day side.
Okay, half of it is always day, half is always night.
Always. The phase we see from Earth is just the daily change in how much of that illuminated day side is visible to us as the moon moves around in its orbit.
So a new moon is when the lit up side is facing away from us.
Completely away. And a full moon is when the entire lit up side is facing towards us. It's all about our changing angle of observation. It has nothing to do with the shadow.
Okay, let's move on to what the moon actually looks like. To the naked eye, a full moon can look, blindingly bright, almost like a giant white spotlight in the sky.
And this is a classic case of our perception being warped by contrast and context.
What do you mean?
When you see the moon against the deep, pervasive blackness of the night sky. Its brightness is magnified. Our eyes, rod cells, our night vision are extremely sensitive to that kind of contrast. So it genuinely feels like a massive light source.
But the numbers tell a different story. What's the moon's actual reflectivity?
The moon is, in reality, an incredibly dark body. We measure this with something called albedo. The moon's albedo is only about 7 to 8%.
Wait, 7%? So it absorbs over 90% of the sunlight that hits it.
Over 90%. Its reflectivity is comparable to, like, a piece of old, worn asphalt, or maybe some dark, freshly plowed earth. The surface is covered in this dark, pulverized rock dust we call regolith.
And that has huge consequences for the environment there.
Massive consequences.
Yeah.
It leads directly to these insane temperature extremes. Because that dark regolith is so good at absorbing solar energy, during the 2-week lunar day, the surface can get up to a blistering 120 degrees Celsius.
Well above boiling.
Well above boiling. But then, because the moon has basically no atmosphere, there's no thermal blanket to trap that heat.
So it just radiates away into space?
All of it. During the 2-week lunar night, the temperature plummets to minus 150, sometimes even minus 170 degrees Celsius.
So these are just destructive temperature swings. So even though it's dark, we still perceive it as mostly gray. Is that another trick of the eye?
It is. It's another trick of low light. Our cone cells in our eyes, the ones responsible for color, just don't work very well in the dim light of night.
All cats are gray at night, as they say.
That's the principle. But if you take a high-quality camera, take a picture of the moon, and then seriously crank up the color saturation in software.
You're basically compensating for our poor night vision.
Exactly. And what you reveal is this stunning geological map painted in really striking colors.
And those colors tell the moon's history.
They tell its entire history. The darker, sort of bluish areas are made of basalt. That's dense rock from ancient, massive lava flows that filled the huge impact basins. We call them the Maria, the seas.
And the lighter parts?
The lighter areas, they take on reddish or yellowish hues when you enhance them. That's a northocite. It's lighter, older crustal rock from the moon's formation. It's chemically distinct. So color mapping lets scientists chart the massive events that shaped the moon billions of years ago.
Okay, so if that's the surface, what about the interior? We have to address this persistent idea that the moon might be hollow, which it isn't just fantasy, right? It has a root in real science.
It's perfectly tied to data from the Apollo missions. During those missions, astronauts set up seismographs on the lunar surface.
To measure moonquakes.
Right. And to test the interior, they needed a powerful energy source. So they intentionally crashed the spent upper stages of the lunar modules onto the surface when they were leaving.
A deliberate, massive impact to create a quake.
Exactly. And when scientists analyzed the seismic waves from those impacts, the data was profoundly strange.
How so?
The sound waves didn't die down quickly like they would on Earth. Instead, they traveled through the moon's interior for a really long time, in some cases for over an hour. This phenomenon, called reverberation, made it seem like the moon rang like a hollow bell.
And that's a powerful metaphor. I can see why the myth took hold. If it rings, it must be empty.
Right. But the reason it rang is the opposite of hollow. On Earth, our seismic waves are absorbed very quickly. Our planet has liquid layers, a molten outer core, a semi-fluid mantle, water in the crust.
Earth is internally wet, and it dampens the vibrations.
It dampens everything. The moon, by contrast, is extremely dry and cold deep inside. It doesn't have those widespread liquid layers. So because it's largely a solid, cold, dry body, there's nothing to absorb that vibrational energy.
The waves just keep bouncing around.
They travel, they reflect off every boundary, and they just keep bouncing with very little energy loss. That's what creates the long ringing effect. It's not hollow, it's just extremely solid and dry.
Okay, that makes sense. The distinction is crucial. But you did mention earlier that while it's not a giant hollow sphere, there are small, naturally occurring voids that could be very important.
Yes, the caves and the ancient lava tubes. These are small pockets of emptiness, likely formed when lava flows drained away, leaving these stable underground tunnels.
And these are a game changer for future moon bases.
The total game changer. They solve two massive problems. First, the 2 or 3 meters of regolith overhead provides excellent natural shielding from cosmic radiation,
Which is a huge health risk on the surface.
a lethal risk long term. And second, the temperature inside these caves is remarkably stable. Instead of those 290-degree swings on the surface, we estimate these voids maintain a temperature around a relatively mild -25 Celsius.
Which requires far less energy to manage for a habitat.
Far, far less. They're prime real estate.
Let's shift our focus now to our home planet and the mechanics of our climate. When you ask people, why do we have seasons? The default answer is almost always, we're warmer in summer because we're closer to the sun.
It's the most stubborn myth in astronomy. That campfire logic closer to the heat is warmer. It's just so hard to shake.
And what makes it so wild is that for the northern hemisphere where most people live, the reality is the exact opposite.
The complete opposite. The Earth's orbit is slightly elliptical. When the northern hemisphere is having summer in July, the Earth is actually at its farthest point from the sun.
That's called a stellium.
Right. And conversely, when we're in the middle of winter in January, the Earth is at its closest point to the sun, perihelion. So the change in distance is clearly not the cause.
So if it's not distance, the entire reason for seasons falls on one single factor.
It's the 23.5-degree tilt of the Earth's rotational axis. That tilt completely overwhelms the minor distance variation. You have to think about it not just as distance, but in terms of energy efficiency.
How much solar energy hits a square meter of ground?
That's the key. When the northern hemisphere is tilted toward the sun in summer, the sunlight hits us at a high, steep angle. It's direct, it's focused, like a spotlight.
Maximum energy per square meter.
Plus, the days are long, so you have more time to absorb that heat. In winter, when we're tilted away, the sunlight hits us at a low grazing angle. The same amount of energy gets spread out over a much larger area.
So it's less intense.
Much less. And the days are short, so it's an issue of concentration and duration, not proximity.
Okay, let's pivot from our steady planetary path to a motion that causes widespread panic every few months. Retrograde motion. It just sounds bad. It conjures this image of a planet just stopping in its tracks, reversing course, and then moving forward again.
And that image is astronomically impossible. Planets cannot physically stop and reverse their direction in orbit. The fear, which is often leveraged by astrology, comes from a fundamental misunderstanding of perspective.
This is where we need that highway analogy again.
It's the perfect way to explain it. Imagine you're on a highway in a car going 70 miles per hour, and you're overtaking a big truck going 65.
Okay.
As you pull alongside and pass the truck, if you only look at your side window for a few seconds, the truck appears to be drifting backward relative to you.
Even though you both know the truck is still moving forward.
Exactly. So on the cosmic scale, the fast car is Earth, and the slow truck is an outer planet like Mars or Jupiter. Because we have an inner, faster orbit, we periodically overtake them.
So retrograde motion is just an optical illusion.
Purely an optical illusion caused by our changing vantage point against the distant, fixed background of stars.
And why does Mercury get all the blame for this? Mercury is in retrograde.
Mercury is just the hardest bright planet to see. It's so close to the sun you can only spot it briefly, low on the horizon, right after sunset, or just before sunrise.
So it's mysterious.
It's mysterious, it's rarely seen, so it has this dangerous aura in the popular imagination. Astrologers seize on that to build fear around its unnatural movement, while easily seen planets like Jupiter are considered more, benign.
Moving now to the limits of what we can actually see, which often fuels conspiracy theories. One of the most common claims against the Apollo moon landings is, if it was real, why can't we see the flags or footprints with our telescopes?
This claim just misunderstands the fundamental limits of optical physics, specifically resolution. The distance to the moon is a factor, sure, 400,000 kilometers, but the real barrier is the Earth's atmosphere.
It's that river of air you mentioned, constantly blurring and distorting the light.
That turbulence puts a hard limit on the resolution we can get, no matter how big our mirror is. Even the biggest, most advanced ground telescopes can rarely achieve a resolution finer than about, say, 1 kilometer.
And an astronaut's footprint is a few centimeters.
Exactly. You'd need a resolution millions of times better than what the atmosphere will ever allow. It's physically impossible. So the fact that we can't see the sights from Earth actually confirms atmospheric physics. It doesn't prove a hoax.
But we do have pictures from space.
Oh, absolutely. The Lunar Reconnaissance Orbiter, or LRO, has been orbiting the moon for years and has taken incredibly detailed, high-resolution photos of all the landing sites. You can clearly see the rover tracks, the descent stages left behind, even the shadows of the flags.
And besides photos, the astronauts left behind physical proof that we still use today.
Yes, the laser retroreflectors. These are basically just arrays of highly precise mirrors. To this day, observatories on Earth routinely fire powerful laser beams at the moon, aiming for those reflectors.
And they time the return trip of the light.
Down to the picosecond. This lets us calculate the Earth-moon distance with millimeter precision. It's an ongoing experiment that provides continuous, irrefutable proof that human-made hardware is still operational on the moon.
Let's talk about another myth, one that actually costs people money. The idea that you can buy the name of a star.
It's a huge business, especially for gifts. But it is, entirely a scam built on fancy certificates and sentiment. Those certificates have zero official scientific weight.
There's only one organization that can actually name things in space.
Only one. The International Astronomical Union, or IAU. Their status is sanctioned by international bodies like UNESCO. If you buy a star name, no astronomer on Earth will ever use it. They'll use its catalog number.
And the IAU has very strict rules for naming different objects, right?
Very specific. Comets are usually named after their discoverers. This encourages people to hunt for them, find a comet, and your name goes in the history books.
What about asteroids?
Asteroids are numbered, but their discoverers can propose a name, a city, a person, an institution, and it goes through a review process. That's the closest an amateur can get to officially naming something big.
But not stars.
Stars are the most boring. They just get catalog numbers based on their coordinates and brightness. Only the very brightest stars we can see kept their ancient mythological names. Sirius, Vega, Betelgeuse.
So the takeaway is, save your money.
Buy a good telescope instead. Join an astronomy club. Try to discover a new asteroid. That's the only way your suggested name will ever enter the official record.
Okay, for our final myth, let's tackle the biggest one in cosmology. The location of the Big Bang. Where did it happen? Is there a spot in the universe we can point to and say, it started there?
The problem here is the analogy our brain defaults to. We think of a grenade exploding. In that scenario, there's a center point, and shrapnel flies out into pre-existing empty space.
And that mental image is just completely wrong for the cosmos.
Completely. The Big Bang wasn't an explosion in space. It was the beginning of the expansion of space itself. There was no outside for it to expand into.
So this is where we have to use the balloon analogy.
Yes, the inflating balloon model. You have to shift your thinking. Imagine the universe is just the two-dimensional surface of a balloon. If you draw dots on that surface to represent galaxies and then blow up the balloon...
all the dots move away from all the other dots.
Right. And crucially, there is no central point on the surface of the balloon where the expansion started. Every point is moving away from every other point.
So to bring that back to our three-dimensional universe... where did the Big Bang happen?
The inescapable conclusion, backed by all our observations, is that the Big Bang happened everywhere at the same time. It happened right here, where we are, and it happened at the edge of the observable universe. The expansion started everywhere, so every point in space can equally claim to be the location where it all began.
All right. We've corrected the record on some fundamental astronomy. Now we're moving from the known, even if it's misunderstood, to the genuinely unknown.
This is where we get into the modern astrophysical mysteries. Things that defy our current models and are pushing the limits of physics.
Let's start with a major recent discovery that has baffled everyone. This powerful, mysterious radio signal that repeats with almost unnerving regularity.
This was captured using the pathfinders for the Massive Square Kilometer Array, or SKA. This periodic radio source was found during testing, and its characteristics immediately set it apart from anything we've seen.
The period of the signal is what initially made people suspect it was human-made interference.
Yes. Early on, it was called the hourly signal, which raises red flags. But the precise period of the pulses is 53.8 minutes. That weird, non-round number argues strongly for a natural process, not a human clock.
And the signal itself is complex. It's not just a simple beep.
Not at all. It cycles through 3 distinct modes. There's a long period of complete radio silence. Then it suddenly starts emitting these powerful, long impulses that can last from 10 to 50 seconds.
And then it changes again.
And then it shifts into a period of very weak, sharp, short signals lasting less than a third of a second. This whole cycle silence, long pulse, short pulse, is extremely hard to model.
But the real physics problem is the period itself. 53.8 minutes. Why is that so impossible for what we know?
We usually look to pulsars for signals like this. They're spinning neutron stars. They spin incredibly fast when they're young, but over billions of years, they slow down.
They lose energy.
Right. By the time a neutron star slows its rotation to a period of nearly an hour, it should be astrophysically dead. Its magnetic field should have decayed, its rotation should be too slow to generate the powerful, defined radio pulses we're seeing.
So if it's not a normal neutron star, what are the leading theories?
We have to consider objects outside the established physics. One idea involves an aging, compact white dwarf. They're the dense cores of dead stars like our sun. Some of them do rotate in the tens of minutes range.
But does the signal match?
Not perfectly. The powerful, defined pulses don't really align with the typical magnetic activity of a white dwarf, which leads to the more exciting possibility.
A completely new type of object.
A completely new astrophysical object. A compact remnant whose energy source relies on a physical mechanism we just haven't discovered yet.
Given how strange it is, you have to ask, could it be artificial?
We always look for natural explanations first. To conclude it's artificial, we'd need to see some kind of structure or encoding, a mathematical sequence, something that suggests intent. Right now, the pulses are regular, but they seem to be a function of extreme physics, not a message.
And we have to remember, we've been here before. History is filled with signals that looked alien at first.
Absolutely. The two most famous are the Maser signal of 1966 and the Little Green Men signal a year later.
The Maser signal was a huge deal because it was so narrow.
Incredibly narrow band. That's the hallmark of artificial transmission, like a radio station. And humans had just invented the maser, so the immediate conclusion was that an advanced ET civilization must be using them to communicate.
But nature got there first.
Nature found a way. Turns out the hydroxyl molecule in dense interstellar clouds, when it's stimulated by intense infrared radiation, acts as a natural cosmic maser. It produces these powerful, naturally narrow beams.
And then just a year later, the LGM signal.
That was Jocelyn Bell's discovery of strictly periodic radio pulses. So precise, like a perfect cosmic clock, that her team nicknamed the sources LGM-1, LGM-2 Little Green Men.
The discovery was actually classified for a while.
Because they thought it might really be a beacon.
The implication was terrifyingly immediate, but the solution was the discovery of pulsars rapidly rotating neutron stars. Not a beacon, but a cosmic lighthouse. These two examples teach us that the universe can create complex, periodic signals that look artificial, but are just extreme physics.
Let's talk about another common misconception. The idea that we can hear sounds from space. We see these videos of the spooky sounds of Jupiter.
This myth is everywhere, but space is a vacuum. Sound needs a medium to travel. You can't hear anything from space directly.
So what are we actually hearing in those recordings? Spacecraft have detectors for radio waves, plasma waves, and magnetic fields. They record the oscillations of these electromagnetic fields. Then, for outreach or analysis, scientists take that data and just translate it into the audible frequency range for our ears.
But does that translation have a real scientific use?
It's surprisingly useful. The human ear is great at picking out patterns, especially sudden, chaotic shifts in sound. For instance, if the translated sound goes from a smooth hum to crackling static.
That tells you something happened.
It immediately tells researchers the spacecraft crossed a major boundary, like the Bow shock wave, where a planet's magnetosphere slams into the solar wind. The sound reflects the physics.
And this was used decades ago to theorize that Venus had active volcanoes.
Yes, the Soviet scientist Leonid Kenfemality. He put a simple storm detector on the Venera landers. His recordings showed frequent, powerful lightning in the Venusian atmosphere.
And he linked that to volcanoes.
He theorized they had to be associated with eruptions. On Earth, big eruptions create intense lightning. Decades later, radar mapping found fresh lava flows and hot spots, proving him right. His sound-based hypothesis was validated.
Okay, let's move to two of the most energetically challenging puzzles we have today, starting with fast radio bursts, or FRBs.
These are radio pulses that last for mere hundredths of a second, but can deliver the energy of 500 million suns.
The shortness of the pulse is the key clue, right?
It tells you the maximum size of the source. For a pulse that short, the source has to be physically smaller than a planet. It requires an object of immense density and energy.
But early on, there was a lot of skepticism, partly because of that famous microwave oven incident.
That's a great story. At the Parkes Observatory, they were tracking these strange, short pulses. They spent years trying to find the source. Eventually, they tracked it. to their own staff kitchen.
Oh, no.
It turned out that when someone opened the microwave door before the timer finished, the magnetron inside would release a short, powerful burst of radio energy.
So their lunch break was creating fake cosmic signals.
For a while, yes, but it forced everyone to be more rigorous. And later, genuine FRBs were confirmed by other telescopes, so we know they're real.
And the leading theory for the source is a magnetar.
A magnetar, a very rare type of neutron star with a magnetic field so powerful it's almost incomprehensible. The energy density in that field is so colossal that a sudden reconfiguration, a starquake, could release that energy in a flash, causing the FRB.
Okay, let's switch to the deepest mystery of all. The X-ray anomaly in the Perseus cluster.
The Perseus cluster is this immense collection of galaxies. It's filled with superheated gas at 100 million Kelvin, so it emits intensely in X-rays.
A perfect target for X-ray telescopes.
Exactly. And when they look at the X-ray spectrum, they see lines for known elements like iron. But they also detected a faint, specific spectral line, a quantum of X-ray energy, that does not match any known atom or process we can create in a lab. It's a line from nowhere.
And this is where the conversation turns to the missing 80% of the universe, dark matter.
This X-ray line is, right now, the most compelling observational clue we have for a particle signature of dark matter. The leading hypothesis involves a hypothetical particle called the sterile neutrino.
Why sterile?
Because it interacts even less than normal neutrinos, which are already almost impossible to detect. It's sterile to most physical forces, which is why it would be dark.
But the theory suggests it can occasionally reveal itself.
The theory suggests that on the rare occasion that these sterile neutrinos collide or decay, they could annihilate and release a photon of X-ray energy. And the energy level of that photon would be dictated by the neutrino's mass.
And it matches the weird line from Perseus.
The calculations for the required mass and the resulting energy line up perfectly with the observed enigmatic X-ray line. If this holds up, it could be the first direct observation of a dark matter particle signature.
We have to end our deep dive into the unknown with the ultimate search, SETI. There's one signal, SHG-B0 plus 14A, that had all the perfect characteristics but with one impossible catch.
This signal was found through the SETI at Home project, and it ticked almost every single box for an ET beacon.
Starting at the frequency.
The frequency was perfect. It was at the 21 centimeter wavelength, which is the frequency of neutral hydrogen, the most common element in the universe. That's the universal channel everyone thinks a civilization would use.
And it had other signs of being artificial.
It was extremely narrowband, indicating a focused transmitter. And most compellingly, its frequency was slowly shifting because of the Doppler effect.
A clear sign of motion. An orbiting planet.
It suggested a transmitter on a planet that was revolving around its star, moving relative to us. Everything looked perfect. It was the ideal signal.
Until they calculated the speed required to produce that Doppler shift.
That's where it all fell apart. The rate of frequency change was so extreme, it required the source planet to be revolving around its star at an impossible speed.
How fast?
40 times faster than Earth orbits the sun.
What does that even mean physically?
It means the planet would either be torn apart by tidal forces or subjected to such extreme stress it couldn't exist. The physics just don't work. The signal had all the signs of being artificial, yet the physical dynamics it implied are completely incomprehensible. It's a truly baffling contradiction.
So what does this all mean? We've covered everything from the fact that we see the same face of a rotating moon to the irrefutable evidence left by Apollo, all the way to these incredible, non-compliant signals from deep space.
The ultimate lesson here is that physics and nature are just far broader than our terrestrial imaginations allow. We debunk the simple myths, but we replace those errors with far grander, more profound mysteries.
Right. We've established you can't buy a star's name, but we found a possible X-ray line that might be dark matter annihilating itself.
And that leads to this final provocative thought for you to ponder. Considering that early radio astronomers were almost duped by the microwave in their break room, what mundane, terrestrial, everyday interference are we currently dismissing as background noise? That could actually be the next great non-compliant discovery. Something for you to think about on your next clear night.
End of the deep dive.